Okay, in this lecture we want to define the dimension of a vector space. So in a bit we'll see that a subspace that is a line will have dimension 1, the subspace that is a plane will have dimension 2, a subspace that looks like R3 will have dimension 3, so on and so forth. So here's the rigorous definition for what we mean by dimension. Our intuition tells us what dimension is. But here's the actual mathematical definition. So just recall a theorem first. We'll let V be a subspace of Rn, and again V could be all of Rn. If V has a basis with k elements in it, then every basis for V must also have k elements in it. So that means that if you hand me some subspace, right, it'll have a basis. That's a theorem we didn't write down, and one we'll probably take for granted, that every vector space, every subspace of Rn will have a basis for sure. So once you write one basis down, say it's got k elements in it, every basis will have k elements. So the number of elements in any basis is the dimension of the space V. So if B consists of the vectors v1, v2 up to v sub k, if there are k vectors in here and B is a basis, then that means the dimension of the subspace V is equal to k. So it's just, the dimension is just the number of vectors in any basis. They're all the same, right? Every basis has the same number of elements. The dimension is the number of vectors in any basis for V. Alright, here are two fundamental examples. So E2, the standard basis for R2, consists of these two vectors 1, 0 and 0, 1. So E2 is a basis for R2. It's got two vectors in it. Therefore, every basis for R2 will have two vectors in it. So that means the dimension of R2 is 2. Right? R2 is the Cartesian plane. It's a plane, and so we would expect that it has dimension 2. And then E3 is the standard basis for R3. So R3 has a basis with 3 elements. That means every basis of R3 will have 3 elements, 3 vectors. And so that means the dimension of R3 is 3. In general, as you might expect, the dimension of Rn is n. So the dimension of R4 is 4, the dimension of R5 is 5, so on and so forth. So these are fundamental examples. The dimension of Rn is always n. You definitely want to memorize that. Let's recast a previous theorem from the last lecture now in terms of the dimension. So remember, V is a subspace of Rn. And if V has a basis with k elements in it, then any set with more than k elements is going to be linearly dependent. So now that we've got this notion of dimension, if the dimension, so to have a basis with k elements in it means the dimension is equal to k. That's exactly what that means. So if you've got a subspace of Rn and you know its dimension is equal to k, then any set with more than k vectors, so m greater than k, this set will have to be linearly dependent, right? So this thing cannot be a basis because it's got too many directions, right? It's got more directions than you need, so you get a dependence relation. So again, if the number of vectors is greater than the dimension, then the set will be linearly dependent. If the number of vectors in a set is less than the dimension, then it won't span. So in either of these cases, we will not have a basis. This is too many vectors, so linearly dependent. This is too few vectors, so it won't reach you won't be able to reach everywhere in the space V using just these directions. So it won't span. If you've got a set with exactly k vectors in it, so if m is equal to k, then maybe it is dependent, maybe not. Maybe it spans, maybe not. So if the number of vectors is equal to the dimension, then you need further testing. All right, so we've seen some examples like this one before. Let's look at some subsets of R3. Which one of these subsets will make a basis? So we know the dimension of R3 is 3, and the reason we know that is because of the existence of this standard basis. We know this thing is a basis, we checked it. And so we know because there is a single basis with exactly 3 vectors, we know that every basis must have 3 vectors. In other words, the dimension of R3 is equal to 3. So every basis must have the dimension of R3 many vectors in it, must have 3 vectors in it. So this thing is not a basis. There's too few vectors, there's only 2. So this thing will not span all of R3. Too few vectors, too few directions to reach everywhere in R3. This thing has 4 vectors in it, 4 is greater than 3. This thing cannot be a basis because we know this set cannot be linearly independent, must be linearly dependent. So 4 vectors in R3 must be linearly dependent. 17 vectors in R3 must be linearly dependent. Right, so this thing is not dependent in R3. And now we get down here to this last one. It's got 3 vectors in it. Maybe it is good, maybe not. Maybe it spans, maybe it doesn't. Maybe it's linearly independent, maybe not. So how can we test whether or not this thing is a basis? Well, it's 3 vectors in R3. And so really, when you take these 3 vectors and make a matrix, call it A, how do we know that these 3 vectors will span? If I pick any B out of R3, I know I can solve this equation. I know this equation will have a solution, right? Well, if this equation does have a solution, no matter what B is, then that solves the span problem. And when is it true that this thing will have a solution no matter what B is? That means the matrix A has to have a non-zero determinant. So this answers the span question. And then this question, is it linearly independent? Well, it's linearly independent if and only if this equation only has the trivial solution. And when is it true that a homogeneous system has only the trivial solution? Well, exactly when the matrix A is invertible. So again, how do we check that 3 vectors in R3 form a basis? Take this thing, write it in a matrix, and then check its determinant. So that's how you test write 4 vectors in R4, build a square matrix and take its determinant. 5 vectors in R5. Build the matrix, take the determinant. So if we look at the determinant of this thing, so you got 1, 2, 3, 0, 1, 0, and then 2, 2, and 7. So I'm going to go ahead and expand along the second column. So when I do that, I get 1, so negative 1 raised to the 2 plus 2 times 1, and then times the determinant of the minor. So 1, 2, 3, 7. And so the determinant of this thing is 7 minus 6, which is 1. So the determinant here is equal to 1, which is not 0. So the determinant of this matrix is not 0. Therefore, these 3 vectors do determine a basis for R3.